Hello there, I'm John Everest, and this is the final, I believe it's the fifth and final part of a discussion on the phase methods for daylight calculation. I discussed how a sky is divided into patches for faster renderings for each hour of the year. I've talked about the 2-phase, the 3-phase. I've just talked about the 4-phase, how it presents the additional opportunity of the additional opportunity of being able to modify the exterior areas of the building you're developing without having to recalculate the exterior or the interior or the glazing. And I've also talked about the cost of the high additional data it generates and the reduced level of accuracy that you need to make sure that the accuracy you are getting from your 4-phase calculation is fit for purpose. Okay, so the 5-phase, and what I'm going to do now is talk about the 2-phase DDS, which is an extension of the 2-phase, the 5-phase calc, which is an extension of the 3-phase, and the 6-phase calc, which is an extension of the 4-phase. And I think a nice place to start is I've sort of kept coming back to these calcs here, but I just wanted to make you aware that whilst you are getting a much faster calculation time, I mean even the 2-phase to just a continuous sky is the savings are, gosh, massive. You know, you're turning a calculation that just for pure ray tracing could take weeks, literally. Into a matter of hours, but the cost is that perhaps where you should be getting a sharp angle, yes, and a view out the window, you simply don't get those. With the 3-phase, it becomes more pronounced. You gain more and you lose a little. You need to decide, is that appropriate? A 3-phase compared to a standard point in time calc, you lose all this detail. Now, imagine you sort of say, well, I want to do many hourly renderings quickly, but I must have these. You know, this is a very important part of my design, and I need to know, is a shadow crisp or not. This is where and it's more about, I need to accurately know the sun patches. You know, when you do like a shadow study, I need to know the sun patches as they move across my building for the day, and having these fuzzy shadows is not fit for purpose. And this is where these other calculations go to. Oh, and that was lucky. I forgot these were here. So the issue is, you know, when you divide up the sky dome into 145 patches. Remember that, how you start off just with a continuous sky, and there are so many areas of the sky to sample there, and you divide it up to make it simpler. The problem with that is for light that's outside, imagine you have sunlight and sky. Imagine it hits a building, scatters, then enters the room. That level of accuracy is fine. But imagine if the light is coming directly from the sky into your room, either from just the sky dome, the general sky dome, or from a sun position. Sky dome, it's not ideal if because then you've generalized, haven't you? Where it becomes a huge problem is with the sun position. So if the sun, and what happens is, because you only have this number of patches available, you only actually have the center of each patch is a possible sun point. Okay, so then you start to, so if your sun, say like on a 145 sky division, if your sun was here, the computer will assume it's here. Yeah, and if the sun is here, the computer will assume it's here. It does a little bit more work than that to sort of make it a little bit more accurate, but the point I'm labouring is there is an inaccuracy. So what you can do is divide it up, yeah, and you can say, well, just divide the sky up more, simple, sorted, and you can keep going, and you can keep going, and you can keep going, and by the time you're at just over 5,000 sky patches, you say, well, yeah, I've pretty much nailed it now. But the problem is so basically each patch is a light source, yeah? So you had 145 light sources to calculate, now you have 5,100 light sources to calculate. That is a huge impact to your calculation time. And the DDS 5 and 6 phase method, what they do is they take this approach and apply it where you need it. So what happens is, okay, so yeah, it's showing you the comparative inaccuracy with because look, your sky, your sun should be that point source there, and that's what you should be getting. But if you just do I would imagine that's just this is probably a two-phase calc with a 1-4-5 sky division. You start to get that, and like I say, it gives you a very good idea of how the sun behaves, but it's not truly accurate. And what you can actually do is there you go. So there's what the actual, that's how it's seeing the sun on a discretized direct sky, but in actual fact it should be that. But it would not be feasible to sort of calculate every single sky patch to the complete accuracy. So what it does is it does the calc first, as before. So there's just with 1-4-5 sky divisions. It then, and this is the case for either the 2, 3, or 4 phase. It's the same for all of them. So it does its first calc as we discussed previously. Then what it does is it removes the rest of the sky and only has the sun as this huge unrealistic point, and it calculates that. So there is no, imagine it's like it would be like there's no atmosphere whatsoever. It is only the direct sunlight that's coming in. So it does this calc, and let's call it like compared to what I'm going to show you, it's a coarse calc, isn't it? It's a coarse calc. So it does that. Then it says, but there's no reflected light, and that's the important thing. There is no reflected light, so it's a very fast calc. It's going to do this for every hour of the year, just straight sun in. So what it's doing is actually picking up the shadows and the direct contributions, yeah, of the coarse sun. Then it repeats exactly the same calculation with a point source sun, yeah, and in it goes. So now you have that very sharp calculation without, and again it does it without any other contributions from the sky. Then what it does is it takes your original calc you did with everything, it removes the light energy from the coarse sun, yeah, the direct sunlight from the coarse sun, and then it adds the direct sunlight from the accurate sun. So what you've now got is the best of both worlds. So the reason it's leaving in the all this here is because it's not as much light energy. It's not as sharp. If it's intersected with exterior surfaces, it's not going to matter. If it's from the sky, it's not ideal. Like from the general sky, it's not ideal, but it is not as significant as this part here. This is very crucial. Okay. And then what you end up with is, there's your original calculation, yeah, that's like this one here, just with everything, with sky and coarse sun, yeah, that's what it looks like. It then repeats that calc only with the coarse sun, with no interreflected light and no no sort of skylight, and you get that. It then does the calc with an accurate sun. It's these two at the same times of the day. Nothing has changed except the sun is represented accurately now as a small sun. And then it says, take the original image, remove the light contributions from the coarse sun, and replace it with the light contributions of the accurate sun, and then you get it. And these are, and because you only did direct sunlight calcs, yeah, there was no interreflected light, these are actually quite quick calculations. It's the indirect component that takes all the time. And then you start to get a, then you can see the sharpness, and you can actually start to get high quality renderings for every hour of the year. And I suppose now I'm literally, there is a little bit more to it where you can actually include they call it the proxy geometry, which is, I'm not going to go into that. I've already been rambling 10 minutes, so I think I've just covered it. And so okay, and the same is with the 6 phase the 6 phase is the 4 phase. You have all this, and then it just does. Here it is with my clumsy son moving through the model. Then I'm going to remove that, and I am just going to do with the direct sun. It is exactly the same. You get the same results. For me, I don't. Gosh, I've never done 6 phase because I did a 5 phase, like just off the command line, and admittedly, if you're just doing luminance values, it's not so bad. But if you're doing rendered images, my word, I have got image files everywhere. And it's just, if you you need to be very, very, very organised to do it in your filing structure. And again, Honeybee does it for you. In fact, whenever I use the command line, but I start off in Honeybee because it will set you off a file structure. And the guy who made the Honeybee plugin is the same guy who wrote this document, so he knows his stuff, and that would be my approach. But anyway, I think that pretty much concludes it. So maybe when you take a look at this, it goes into all sorts of it goes into all sorts of detail, and there's lots of helpful sort of images and stuff like that. You can make these images yourself via the Ladybug plugin for Grasshopper. Yeah, but all the discussion is around this, and there's I'm doing all this on the fly, but you can see how as you use more patches, your actually increases, as does your calculation time, and that's what good analysis and good design is, isn't it? Is like how can I get sort of like 80% of the accuracy for 20% of the time, and that is the very concept of like climate-based daylight modelling. It's huge savings with the vast majority of the accuracy, and you just need to be aware of where the corners are cut as I've tried to sort of labour to you, so you know when it is or is not appropriate, when you could use a 3 phase or you need to move to a 5 phase. Okay. Yeah. Okay. I hope that was useful. Thank you for listening, and good luck trying that yourself.